Now look, so far we discussed situation where we have null hypothesis and then we test it, right? So we compare how our sample is extreme or not extreme for the null hypothesis, and then we either reject or accept null hypothesis. And in these apps, we discussed also that the significance level, it's the value you compare your p-value with. It's a chance to make a wrong decision. It's a chance to reject null hypothesis, although the null hypothesis is true. And in science, null hypothesis is most of the time, it means no effect. So it means that if null hypothesis is true, it means you don't have an effect. So for example, medicine doesn't work, or maybe this factor doesn't influence the outcome, and so on and so forth. So it means that when you reject null hypothesis, you claim that you see an effect. And it means that you sort of can make some wrong decision. So you claim that you have an effect, but also it doesn't. You don't have it, right? So it means that, for example, medicine, you say, oh, medicine works, so it treats this disease, but it doesn't. And that's kind of a problem, right? The question is, okay, if we take this significance level small enough, like 0.1%, so we reduce this error of making a wrong decision, but can we recognize the effect if it's present? Because we have also another situation when effect is present, so it means null hypothesis is wrong. But you are not able to see it because your significance level is too small, for example, right? Can you handle this type of error? You can, and that's what we are going to talk about in this app, right? So what you see here, the blue distribution in this big plot, what is real population looks like. So the real population, you can see that it has the chloride in water, approximately 105 milligrams per liter in average, okay? However, our null hypothesis is that the chloride in this water is 100 or less. Imagine that 100 is a kind of maximum acceptance limit. So we believe that for example, we are talking about lake, we believe that our lake is not contaminated. So this is our null hypothesis. Mu is 100 or less, but in reality, the lake is contaminated. Can we see it by making a hypothesis testing? Can we reject null hypothesis? This is the null hypothesis, right? So we believe that the reality is gray, but in fact, the reality is blue, right? So our sample came always from the blue population, not from the gray. But you can see that the populations, the reality and our expectation from the reality, they are overlapping. So sometimes you may accept null hypothesis, you cannot reject it because they're heavily overlapping. How often you will do that, and which factors influence this chance that you will make this type of error? So let's talk about that. Well, first of all, you can see that in my case, my sample mean is 105. I believe the population mean is 100 or smaller. My sample mean is 105, and this is standard deviation of my sample. So if I compute a p-value, I got a very, very small number. You can see it's less than 1%. So if I work with significance level 5%, I will reject null hypothesis. In this case, it will be a correct decision, right? Now look at this plot, what you see here. Here you see the expected sample mean, right? This is the reality, and this is your null hypothesis. So you believe that your sample mean should be somewhere here. But in fact, your sample mean will be here. So how often you will reject your null hypothesis? If your sample will be somewhere here, or somewhere here, or somewhere here, or somewhere here, you will reject null hypothesis because this is the direction of extremeness in this case, right? So in this case, this is my sample. You can see the chance, if we believe that this is true, the chance is very, very small that sample will be here. So therefore, we reject it, right? We can compute how often we will reject null hypothesis in this case, and that's what we call a power of test. Okay. So the power of test is actually an area. If you think about 5% value here, so all area on the right, it's a power of test under this blue curve. Okay. So in this case, you can see the power of test is 95. So it means that in 95% of the cases, I will reject null hypothesis. Let's check it. Again, if you take a lot of samples, how often I reject null hypothesis? You can see that I took 23 samples, and in 22 of them, I rejected null hypothesis. My p-value was quite small. I mean, smaller than 5%. So it gives me that 95.7% rejection rate, and that's the power, right? Again, I will get 95 exactly if I keep going, right? So that's the power of test. How to increase or decrease the power? Apparently, the sample size in this case influences the power. So if I, for example, take a bigger sample size, you can see the power is 99.5%. So it's almost impossible to accept null hypothesis in this case, right? Only 0.5% chance that I will accept it, right? And then, for example, if sample size is 20, that it's even less likely that I will accept null hypothesis. The power is very large in this case. So sample size is important if you want to see also if you want to see an effect if it's present, right? The second important thing is the effect size. So if, for example, the reality is not that far from your null hypothesis, you can see that the power is getting smaller, right? So if you want to distinguish between 101 milligrams per liter and 100 milligrams per liter, which is our null hypothesis, you need even bigger sample size if you want to have a bigger power. For example, if sample size is 40 in this case, so you say, for example, 40 glasses of water, your power will be approximately 58%. So the chance to reject null hypothesis will be approximately 58%. So the idea is following: the smaller effect you want to distinguish, the larger sample size you need. Okay. And finally, one more thing: even if effect is large, the variation of your values, how homogeneous or heterogeneous your population is, also influence this. Because if you have a large variation of your values, you can see that uncertainty is getting also larger and the power is getting smaller, right? So in this case, for example, if I have a sample size of 10, you can see the power is 77.7, although the effect is pretty large. You can see that the means of the populations are pretty far away from each other, okay? So this is the power of test. So the power of test tells you a chance to see an effect if it's present, to reject null hypothesis if it's wrong. And the power depends on many things. It depends, of course, on significance level as well, but keep significance level as small as possible to reduce type 1 error chance. And then, depending on the effect that you want to see and the variation of your population, you need to define which sample size you want. For example, if you want to increase the power, you need to increase the sample size, right? So it's a kind of a trade-off. For many tests, you can compute the desired sample size for given effect size and for given, for example, significance level and standard deviation. So that's what be my advice. So before you start your experiment, set significance level as small as possible, define the size of effect that you want to distinguish, approximately estimate the standard deviation of your population, and then simply compute the sample size, the desired sample size for the power that you need. Okay. So once again, play with this app and then hopefully you will get a better understanding of the power.